All right, yeah, thanks for the invitation. So yeah, do feel free to interrupt with any questions. I might go a bit fast because I want to get to lunch, but hopefully, yeah, should do that. At the expense of doing work, so do ask it. All right, so yeah, since I put Liouville quantum gravity in the title, I guess I need to explain what that is for me. For me, it's a random metric measure space, parameterized by some domain in the plane. So here's a picture. So we've got squares of different colors and sizes, or different Euclidean sizes, I should say. Because the idea is that the LQG area of each of these squares is supposed to be roughly equivalent. So this is a picture of what we're doing.
Please louder.
All right. Okay. I can't see one in my vicinity, but I can just shout. It's fine.
You're finishing off.
I mean, well, it might hinder us in other ways, right?
So you keep it short then, right? I think it's a bit better, no?
I don't know what this ground from the crowd was. Like, was that good or bad?
So you start complaining and we put it back then, okay? Please.
All right. Let's see. Okay. Yeah. Next point. LQG is supposed to be a random Riemannian metric. Okay, the scare quotes for a reason, but and the metric tensor, again in scare quotes, should be given by exponentiating the Gaussian free field on a domain. I also want to at least mention that this is equivalent to the Liouville CFT, but short of like flashing up the Liouville action. I'm not going to say any more about CFT, so I'm sure we'll hear about it later from some other people. Again, right, the GFF itself, again, I probably want to sort of glide fairly quickly over the, hopefully most people are sort of more or less on nodding terms with it. So what do I want to emphasize actually? So I want to think of it as the standard Gaussian with respect to this directly inner product, and this is the laser, there we go. So this inner product is conformally invariant because we're in 2 dimensions, and that makes the field conformally invariant. I guess, yeah, I don't want to say too much fine detail about the difference between the zero boundary field and the whole plane field. I think my purpose is I just wanted to put this this definition with the series up, a sort of intuition for the fact that we have a Gasanov type result for the GFF. So I have this sort of spiky, random looking field, and the idea is that if I add a smooth bump function to the field, the resulting object has a mutually absolutely continuous law with respect to that of the original field. Okay, and the other property of the GFF that I need is the domain Markov property. Let's take this sort of square and let's imagine that this square is sort of within the whole plane. So if I had a whole plane GFF and I observed the values outside this square, then conditionally on what I've observed, the law of the field within this square is going to be given by the harmonic extension of sort of the boundary values of the field plus an independent GFF inside the field. Okay, so that's the domain Markov property. Okay. And how's the pace? Is this all right? Do we have any questions? Okay, you nodded to say no, we don't have any questions. Okay, that's distracting. Right. Okay, so now I introduce the LQG metric. So this was introduced by Polyakov in the 80s. Again, I want to say that it's a Riemannian metric given by exponentiating the Gaussian free field, or gamma times the field, where gamma is a parameter between 0 and 2. And okay, so since the field doesn't take pointwise values, this doesn't make literal sense. So in order to construct this, what you have to do is you have to mollify the field somehow, and then do first passage percolation with respect to the exponential of this mollified field. So I mean, the length of the path is going to be the integral of something like this with the mollified version. And when I say something like this, I mean, for a Riemannian metric, you'd want to put gamma over 2 here, right? So gamma is the exponent for areas. So you'd think gamma over 2 might be the exponent for distances, but it's not, because it turns out that this thing should have Hausdorff dimensions strictly bigger than 2. So instead, you have to put gamma over a mysteriously defined d gamma to do your first passage percolation, and then get subsequential limit, which is our LQG metric. But once that's done, the result is so it's a metric that induces the Euclidean topology, so that's sort of nice. It's a geodesic metric, so there's a geodesic between any 2 points, and we have this important property of Weyl scaling. So again, if I add a continuous function to the field, what does the length of a path with respect to the metric defined from h plus f look like? Well, I integrate the exponential of this function f over the path, which I've parameterized at unit speed with respect to the metric for h. So this is sort of a natural thing. If you sort of imagine that h is a smooth function, this is sort of naturally what paths in the metric with respect to h plus f should look like versus the metric with respect to h. So okay, so this is that's what I want to say about the LQG metric for now. So I also want to. So I've parameterized these LQG objects by a domain in the plane, but I don't want to consider that parameterization as canonical. I want to consider these things up to conformal changes of coordinates. So here I have to be careful because okay, the GFF is conformally invariant, but obviously when you do a conformal map, the Euclidean areas and distances change. So if I want to preserve the LQG areas and distances under this reparametrization, I need to modify the field somehow to account for what the conformal map is doing to the Euclidean geometry. So here's the formula. Okay, it maybe looks a bit different from what you'd expect if h was a smooth function. Okay, so when you do a conformal map phi, then areas change by phi prime squared, right? So e to the gamma times a smooth function should change by So you should change by 2 over gamma. So 2 over gamma times that should give you that factor of 5 prime squared. So for the GFF, there's a bit of an extra term, and that's just coming from how you have to regularize the field, how you have to scale regularizations to get something sensible in the limit. So okay, so it's a little bit different. But once you've done this coordinate change, then the conformal map preserves the LQG distance, and it preserves the LQG area, which is, so this is intuitively like the area measure whose density is given by e to the gamma times the field. Okay, and again you have these regularizations, so you get this extra term. And okay, so we now know that the area measure and the metric are sort of compatible with each other in the sense that the area is, you can recover the area from the distance as a Minkowski content. Okay, yeah, so there's our regularization. So gamma squared over 2. Right, it's gamma times this. So there you go. All right, so I guess, yeah, the moral of this slide is just to emphasize I'm considering these objects as sort of abstract surfaces in some sense. So like, you have a parameterization by a complex domain, but you don't care which domain it is, because you can do this conformal reparametrization. So you have a conformal structure without having a single canonical embedding. All right. So yeah. So why are these interesting from a probabilistic point of view? Well, I guess it's a continuous object, so it should be the scaling limit of a discrete object. So yeah. So our example is going to be random planar maps. So by a planar map, I mean a planar graph that's embedded into the plane, and I choose the embedding, or I choose the homeomorphism type of the embedding. Okay, and I guess the first of several like scaling limit results is this result of Legala-Meermont independently, which is that if you take a uniform random quadrangulation, so that's a random planar map where every face has 4 edges, then the graph distance converges in the scaling limit to LQG with gamma equals square root 8/3. But of course that's not how they stated it. So okay, it turns out in this case gamma equals square root 8/3. The LQG metric is actually equivalent to a Brownian surface. So this is a completely different construction where all the distances are sort of explicitly described via Brownian motions. Okay, and this is a very special case that you can't get this from the values of gamma. Okay, but that's maybe the first of these sort of scaling results. I want to talk about another, and so here the planar map is this what's called the mated CRT map. So it comes from this mating of 2 continuum random trees, but you discretize it. So this is our map in the end. Here are our random trees, and how do I get from here to here? So the vertices are going to be these vertical strips, strips that are next to each other, adjacent by these red edges, and the green edges correspond to horizontal line segments that either stay above this contour function or below this one. Okay, so I glue together. So I draw edges between correspond to these green lines here, and then I get this. What turns out to be a triangulation. Okay, and I should say where the gamma is here. So the gamma of the LQG is in the correlation between these two Brownian excursions. It's something like cos of pi gamma squared over 4. Something like that. Anyway, so here, these things we know convergence to LQG in a few different senses. And the one that's of interest here is that you can somehow do a discrete conformal embedding of these maps, and then that converges to LQG. So what I mean by a discrete conformal embedding here is what's called the Tut embedding. So firstly, I have a boundary in this map that I'm going to embed onto the circle in such a way that a random walk on the graph should have sort of roughly uniform hitting distribution. And then the interior vertices are going to go in a sort of harmonic way. So each interior vertex should go to the center of mass of its neighbors. And given the boundary, given where the boundary vertices go, you can always do this in a unique way. I promise. And so this sort of discrete conformal embedding, it turns out to converge to LQG in the sense that the uniform measure on the vertices goes to the LQG area. Okay, so what I'm trying to get across about this result is that you're really seeing this object as the limit of a discrete conformal object.
Wait, how do you define the boundary vertices in the naked CRT map?
So I've sort of drawn. Yeah, so I've sort of got this picture that doesn't really have the boundary.
But you pick some exterior face or something?
Yeah, exactly. Yeah.
Okay.
Yeah, okay, so maybe this wasn't the best choice. But I guess the boundary would be sort of the vertices that have these orange lines here.
Mm-hmm.
Okay, so they're sort of connected to the outside.
Mm-hmm.
So, yeah, whatever it is, this one, and this one are going to be the boundary. Okay. Right, so yeah, so the upshot of the previous slide is that this embedding of an LQG surface into the plane or the disk in our case, because we had a boundary. So this is a scalar limit of discrete conformal embeddings of some objects, which are random planar maps. So the question is, can you see this at the level of the LQG metric? So we can ask, is the identity map from the LQG metric on a disk to the Euclidean metric conformal in some sense? Okay, so the first question to answer is what should conformality mean here, because we've only got if I'm only looking at the metric, I'm sort of forgetting the conformal structure such as we had. So one sort of natural thing to try, I guess, is you ask for the map to be quasisymmetric. So this means that the ratio between side lengths of a triangle doesn't change too much. So it's controlled by this psi, which is just a function of the ratio. So right. So this is what quasisymmetry means. So the reason I'm proposing it as an answer to this question is that if you have subsets of Euclidean spaces, then a map that's locally quasisymmetric is equivalent to one that's locally quasi-conformal. So if you don't know what a quasi-conformal map is, probably the easiest way to think about it is that infinitesimal circles are going to map to infinitesimal ellipses where the eccentricity is bounded. Okay, so distorting circles by not that much is sort of equivalent to distorting triangles by not that much. Like when. Okay, so you can also define quasi-conformal maps of the complex plane using this Beltrami equation. So this Beltrami coefficient is supposed to be strictly less than 1. For a conformal map, it would be 0. Right. A conformal map sends circles to circles. And here we're allowed to sort of stretch the circle a bit, but not too much. Okay. Right. So, so it turns out this is a result of Troscheit that in the Brownian surface case, square root 8/3, not only is the identity not a quasi-symmetric embedding, there isn't any quasi-symmetric embedding into any finite dimensional space, in fact. So the idea, this isn't quite how he phrased it, but the idea is that in the LQG metric, you can find what I'm calling cliques. So you can find arbitrarily large sets of points such that the maximum of the pairwise distances between them is bounded by some constant that doesn't depend on the number of points times the minimum of the pairwise distances. So, I mean, like, if you think about it, this definitely does not happen in a finite dimensional space, right? Because, okay, you put like n sort of small balls around each of these points, and they all fit into a ball of radius this. Okay, so you're fitting arbitrarily many balls into a ball of, k times the radius, or 2k, or 4k, let's say, to be safe. Times the radius, and okay, by looking at volumes, this does not happen, right? So equivalently to the existence of these cliques, the metric is not what's called a doubling metric. So the doubling metric is one in which every ball can be covered by a constant number of balls of half the radius. And okay, sort of intuitively that this is telling you that this doesn't happen. There's also a notion of dimension called Hausdorff dimension, which sort of quantifies it sort of quantifies like what time you need here. So so a metric is doubling if the number of balls of radius little r needed to cover a ball of radius big R is polynomial in big R over little r, and the exponent you need here basically is the Hausdorff dimension. And of course, if you're not doubling, then there's no exponent that works, so your Hausdorff dimension is infinite. Okay, and the thing about this property of being doubling is that it's preserved by quasi-symmetric maps. Hopefully that makes sense. I mean, your M is, so this is just concerned with these ratios between distances and then the quasi-symmetric. The quasi-symmetric map sort of changes this, but only by a known amount. So being doubling is preserved by quasi-symmetric maps. So this isn't doubling, this is, so no embedding from the first to the second can be a quasi-symmetry. Okay, So here, finding these sets of points used the sort of the Brownian surface stuff. So, but at this point, it's perhaps not surprising that you can do the same thing for any gamma, just with a different method. So again, you can find these sets of approximately equidistant points, which is enough to dash all hope of there being a quasi-symmetric embedding into sort of anything nice and finite dimensional. So here's like a quick idea of the proof. So you draw a star with n points. So here n is 4, and you want to say, so I want to find points in each of the arms of this star, so that geodesics between these points have to sort of stay inside the star. And if I do that, then all these points should so all these geodesics should accumulate sort of similar amounts of length, which is going to make them approximately equidistant. Okay, so how do I force these geodesics to stay in here? Well, what I can do is if I add a bump function that's massive, sort of outside the star, then okay, I get a different field, but I use this file scaling property to say, okay, if the bump function is sort of massive outside here, then geodesics don't want to leave the star because they'll accumulate far too much length. So that in this modified field, there should be this clique of approximately equidistant points. Okay, and so if that happens for the modified field, then by this Gasanov theorem for the GFF, it happens with positive probability for the original field because the laws are mutually absolutely continuous. Okay, so that gave me this thing with positive probability, which of course is not enough. But everything I did was sort of local to this sort of disk here. So, so the next thing I want to do is sort of say, well, I have positive probability of finding the thing I want in a given disk, and by the Markov property for the GFF, you know, once I've seen this, it doesn't really affect what's going on in some other region. So the near independence of the field, sort of in different regions of the domain, is going to allow me to do some kind of Markovian exploration, and since I have constant positive probability of finding this thing, you know, in any place I look, eventually I'm going to find it, almost surely. Okay, so yeah, so really I've just used this sort of Weil scaling property and the Gasanov and the Markov property of GFF. So in some sense that's maybe not really that much. I mean, so it sort of suggests that maybe if you have any sort of stochastically self-similar metric space where there's enough randomness, that's probably enough to break the doubling property. So I suspect that there should be a more general result along these lines, but I don't quite know what that is yet. Okay, another sort of direction which which you might be heading in is, maybe they just took the wrong definition of conformal, right? Maybe quasisymmetry is like too strong because you just need these really local things to break it somehow. So, maybe this is the wrong question, and there's some other way in which the embedding I get is like conformal. Another thing, I mean, we're maybe heading sort of further away from things that have applications, but another thing you could ask is, okay, what about if I try and embed into an infinite dimensional space, right? What if I try and embed into L2 or L1? I mean, how nice can an embedding of the metric into an infinite dimensional space be? And this is something that I've been thinking a little bit about recently. And one thing, I mean, this is almost like fully combinatorics now, so it might be, but like, what about like trying to embed a random planar map in such a way that we have some kind of tightness and we can take a scaling limit, and that I guess leads us to some long-standing open problems, I guess. Just in the study of metric embeddings of graphs. So yeah, for example, like it's conjectured that the graph distance in every planar graph should embed into L1 with distortion, with constant distortion actually, which is still not known. So into L2, like for general planar graphs, it's square root log n is the optimal, but I sort of suspect that if you have a random planar map, typically you should be able to do better than square root log n. So here n is the number of vertices. I think one can at least do better for random regulations, but that's modulo some quite painful like combinatorial enumeration that I haven't been able to get through yet. But anyway, if anyone likes random planar maps, or if anyone has like a better idea than quasisymmetry for what these conformal embeddings should be, then yeah, we can talk. But yeah, that's me for now, I think.
Thanks.